In the previous module on encryption, we introduced the ideas of basic encryption, asymmetric encryption, symmetric encryption, and a public key infrastructure. This module will talk about a specific application of some of these techniques using the secure sockets layer or transport layer security. We want to introduce this concept. We want you to understand what it does for us in a mobile context and understand how we use it. So transport layer security, TLS, or SSL, secure sockets layer, are functionally the same thing. This began in the early days of the internet. When commercial use of the internet became acceptable, people wanted to be able to do usual, normal commerce over the internet. And that left two challenges. Number one, how as a user can I determine the actual identity of the website that I'm visiting? Does the name Amazon.com actually have a link to a company called Amazon? It exists in the real world. And then, when I make payment information or enter other sensitive information, how is it protected from observation, capture, or manipulation when it is being transmitted from my browser to the server? So SSL, the secure sockets layer, was originally invented to solve those two problems, identity and privacy. SSL became popular with version 1, which was developed and used internally at Netscape Communications. The public release was version 2.0, and as it became popular and successful on the internet, it was revised to address some problems and became version 3.0. As it became more widely adopted, Netscape released SSL into the public domain and turned over stewardship and maintenance of it to the Internet Engineering Task Force, or the IETF. The IETF renamed it and enhanced it slightly, calling it TLS for Transport Layer Security. Remember, at the beginning of the security discussion, we talked about the fundamental difference between wired and wireless communications. That the difference is the ability or the necessity to access the media to get to the bits. With wireless, if you can hear my voice, you're in radio range, so you can access the bits as they are being transmitted. The original designers of IEEE 802.11, otherwise known as Wi-Fi, and of the GSM protocols built in encryption at the physical layer to protect the confidentiality and integrity of our data as it's being transmitted. But as the user and as the administrator in the data center, we have no control and indeed cannot even reliably determine if those connections are encrypted when they're actually in use. So we impose our encryption at a higher layer of the network stack where we do have control, the transport layer. Unless we get into a really complicated discussion, we really can't functionally make a distinction between SSL and TLS, so we'll use the terms interchangeably. Understand, though, that if you are programming or configuring your application, you should never use SSL older than version 3.0, and you should use the most current version of TLS, currently TLS 1.3. So let's look at how it actually works. SSL and TLS do two things. They authenticate the identity of the server to the user. They do this by using a digital certificate, a signature, a certificate which binds the identity or name of the website to its address. This is digitally signed by a certificate authority, as we discussed in the previous module on public key encryption, or public key infrastructure. Secondarily, once I have distributed and identified the website and distributed the website's private or public key to the user, I can use that public key to encrypt a session key and send it back to the website. Then, using that session key, now only held by the user and the website, I can encrypt the communication, therefore fulfilling the second role of SSL. In special circumstances, if we have provisioned digital certificates for the user can also use his public key to identify himself to the website. In practice, this is rarely done. Applying the STRIDE threat model and attack surface analysis, considering the data, method, and channel, we can see that spoofing, tampering, and information disclosure are threats that apply to the channel. And HTTPS or SSL or TLS, all these terms are used interchangeably, can be used to mitigate against information disclosure and to partially mitigate spoofing and tampering. Let's look at how that works at the low level. The client initiates the connection with the server. It sends a hello message which contains the SSL or TLS version number in use, the cipher suites supported, an indication of whether the data will be compressed, and some other session information including a random number. The server responds by sending a hello certificate or hello message containing a signed digital certificate. The client validates that digital certificate, verifying the digital signature and matching the CNAME contained in the certificate with the name of the server visited. If the certificate is valid, the client will generate a random session key, encrypt it with that public key supplied by the digital certificate of the server, and transmit it back to the server. At this point, the identity of the server is assured to the client, and they both have a copy of a unique session key to be used to encrypt further communications. In an extended example, if a client certificate is present, the client can send their digital certificate to the server can likewise validate it and determine with some trust the identity of the client. This is logistically challenging. It involves creation and distribution of client certificates for every user, so it is not often used. When should we use SSL and TLS with mobile applications? The answer is simple: always. We always want to ensure the identity of the server to our client applications, and we always want to encrypt the data in transit between our client applications and our server, because we cannot depend upon the physical layer encryption of GSM or Wi-Fi being present, activated, and properly configured. At the very minimum, use SSL TLS for critical functions, logins, for all exchange of sensitive information, and all authentication data. What can go wrong? Well, look at this picture. And here you'll see a really nice bicycle locked to a post with an expensive lock and a heavy-duty chain. But if you look closely, you'll realize all an attacker would have to do to steal this bicycle would be to walk up, flip the chain over the top of the post, and ride away. The defender, the owner of the bicycle, didn't even run the cable through the front wheel or the rear wheel of the bicycle, so a thief, the attacker, can steal the bike using its own mechanism. He can ride it away. This is a perfect example of a good tool not being used properly. So, you must use SSL correctly, proper versions, and properly validate certificates. You must also choose your certificate authority carefully and ensure that the public key for your certificate authority is pre-installed in the browser or operating system of your clients. Otherwise, they will not be able to validate those digital certificates or the identity of the server. In the process of validating the certificate, the client will on occasion see errors. Here's an example of some of the errors that may appear. Now, as a user, you're used to this and probably don't realize it. When you visit a website, try to use a secure connection, and a window pops up that says there's a problem with the certificate. One of these error conditions has occurred, and the operating system or the browser is notifying you of this error. The key is to test for these errors and to handle them. It's vital that you understand, as a mobile application developer, the tasks normally performed by the web browser, validating the certificate, using the SSL, now are your responsibility. You as a developer or the security professional must ensure that you are using the SSL, using it correctly, validating certificates, and handling errors. So, the checklist prior to deployment in the testing phase of the development lifecycle. Use SSL always. Avoid using mixed modes. It's possible to use SSL for part of your communications and to transmit other data in plain text. We recommend that you avoid that situation. It's just simpler to encrypt everything. Verify and validate the certificates. The key thing to validate is that the CN or canonical name or CNAME contained within the digital certificate matches the domain name of the site you're visiting or the server you're connecting to. Know the SSL errors and handle them. Understand that it is your responsibility as a developer or security professional to handle these errors, to implement the SSL and use it correctly. The browser won't be doing it for you. Verify the certificate authority is pre-installed in the clients that you are going to support, in the client operating systems for the 4 mobile platforms. Verify the server side, the configuration. Test. Never assume it just works. And remember the Heartbleed vulnerability. This was in the OpenSSL library. Approximately 2/3 of the public internet used OpenSSL in one form or another when this vulnerability was discovered. Design your applications so that you have flexibility to replace components like your SSL library should a vulnerability be discovered. Thank you.